my life, I've been following Paul. When I was a student, the first paper I read by him was this one on Pontryagin polynomial residues of foliation singularities about the homotopy type of big gamma. And I'd never met Paul, but this paper was very encouraging because it meant what my thesis was doing was maybe of interest to somebody else. Then later, a couple of years later at the Institute in Princeton, I met Paul, who was there for the year. And we ran a seminar along with Larry and James Heitch and some others. So it was very, very supportive. And you're starting out in, I think I misspelled Paul's name there. So Paul has always been encouraging of work in foliations, and I've never, I hope, not let him down. Because here we are, 40 years later, and still talking about these things. So, yeah, it's, and other people think it's boring, but it's always fascinating. So, I have to confess that the paper I read was not Paul's main work. In fact, I didn't really run into Paul's main, what he's famous for, until we were at a seminar in the evening in Tokyo, and they were explaining what Paul had shown in 1974, 20 years earlier, where he constructed a counterexample to the Seifert conjecture, theorem I'm sure everyone knows. So this result, is a beautiful result, and Paul had generalized it, but my interest was homotopy theory type things. And so it wasn't until we had this seminar where all of a sudden the meaning of this problem popped up, at least for me again. And I just wanted to recall, to explain what was going on, that what Paul had done is taken an idea of Wilson from the 60s, where he took a flow on a 3-manifold and inserted these plugs. I hope the picture makes it look like a plug, because it's an annulus cross an interval. And he used the attracting to a periodic orbit to force the flow to modifying it have only 2 periodic orbits, because you could do this process over and over until you reduced it down to 2, which didn't solve the Seifert problem, but said you could attack the problem somehow. And the idea that Paul had was that, well, the circle, it's a circle, but maybe you could replace it with something else. And I don't know where the idea popped up from, but he had the idea to put in a Dangerois minimal set. Now, that's not easy to do unless you take the torus, which carries it, but the minimal set has an open complement, so you could take out a point and get the surface you see. And now the flow, and I didn't try to draw it, I stole the picture from Paul's paper, copied it. Now the flow goes into this plug, looking like a ring, double ring, and spirals around forever. And as it goes vertically, the trapped orbits spin around. They approach the suspension of the Cantor set, and they have a holonomy because it's a flow, and the holonomy has no fixed points. It's a translation on the Cantor set. So this was a very, very clever idea that gave a C1 counterexample to the conjecture or problem stated by Seifert. So that's the history, and everyone I'm sure has seen this before. And what the seminar did was examine a paper that had arrived either with Gis, Etienne had it, or somebody arrived to this conference with a manuscript that Christina had sent out to 60 people, I think she said, of her construction of a smooth counterexample. Now, there's a lot of history to this, and it's fascinating because of the drama in the fall of 1993, as this paper made the rounds and was presented in seminars in Berkeley and everywhere. So we had a seminar, and it's a beautiful example, but it has a different principle. So I'll describe this again. Probably everyone's seen it, but maybe not. So this also appeared in the annals, but 20 years after Paul's example. So what did she do? Well, this is the part that I recently learned because we wrote, Anna Reckman and I wrote this article for this website, Celebratio, on Cooperberg's work. And I called it Cooperberg Dreams because it also talks about ideas and what could possibly happen. But Christina explained that she was thinking about this question of why you have to have a fixed point, and stated that, well, if you have a flow that takes a disk to itself, it's going to have a periodic orbit. It's going to have a fixed point for the return map. And so you need an action that doesn't preserve a disk, that has a holonomy that is a translation. Now, I guess you can always look back and say this is somewhat, I won't say obvious, but logical. And I call that the Cooperberg principle. I don't know if it's a principle of what, but it's basically aperiodicity means your holonomy is a translation in whatever sense that means. But of course, it wasn't just an observation, because I recommend the article because I have a lot more quotes from Christina in it. But she had the idea that you could achieve a translation from the last slide, not this one, not that one, but this one, where the flow going up is attracted to the periodic orbit, but never gets there. So it's a translation on those flow lines. So if you were somehow to take your orbit and have it intersect that vertical climb, you would get something without periodic orbits. Well, I had not heard her explain how the example was built. We had only analyzed it. But we do not want to jump call. So the summary was Wilson had the idea to trap the flow and send it all spinning around circles. Paul had the idea to trap the flow in a little dramatic death spiral into a continuum, which is the Daljois minimal set. Well, back off one more step, and Christina had the idea to send the orbits into a death spiral, but you don't know where they go. So she constructed a flow, but we can't say what the minimal set looks like particularly. And that sort of becomes fascinating because dynamics, you want to analyze it. At the minimum, you want to know what the minimal sets are. So let me explain this. Those are the strategies. Here's how, this is quick if you've never seen it or review otherwise. Here's what she did. She took the Wilson plug and she modified it by having all the orbits climbing up. The subtlety here is that the two orbits are in opposite directions, the two periodic orbits. And so if you perturb this, all those orbits are going to break open. It'll just flow up. I don't know if that's a critical idea, but the critical idea is that with this orientation for the flow, what you can do, what she did, is take this picture, stretch it out. It's a little bit of a jump, but you just take the annulus and warp it, much like Paul warped his surface. And I've drawn the flow lines I think this is probably from her paper, but it might be from my paper with Anna. I'm not sure who owns this picture. You stretch it out, and then comes the fantastic part. You insert it into itself. And now, because of the way you've oriented the flow, you find that you can insert it smoothly. And what's missing in this picture is all this notation, the face E1, entry 1, E2, is that this E1 is the bottom of the plug. So it starts going in and spinning, climbing up the Wilson flow as it goes up to its periodic orbit. But before it can get there, it's going to hit the insertion again. And so she built into this example a recursion process which goes forever. Now, proving that this is aperiodic takes a bit of clever work, and there's several papers explaining it by Etienne and by Shigenori Matsumoto. But it's a beautiful, beautiful construction, and I guess you'd say just simplicity itself. I think Christina's quote was, once you see it, you see it. Okay, took me a couple of maybe 10 more years. But this was her idea, and so smooth examples were produced. Later work, I think Thurston or Sullivan remarked, oh, it can be made analytic, real analytic. And so you get a complete solution to a counterexample. There's smooth, real analytic flows without periodic orbits on any oriented three manifold. So this is the background. This is the history of what I want to talk about. And you could ask, is that it? So why study aperiodic flows? Well, on one hand, and this is the question I certainly asked, because Anna Reckinen came to Chicago when she and Pierre P. had postdocs in Chicago, and I think in 2009 or 10. It's a long time ago. And she had written a thesis on the analytic examples and proposed we study these. So why study them? Well, aperiodic flows are exceptional. I like the Nassau flows. I like compact group actions. Well, these are neither. They're neither hyperbolic nor elliptic. They're parabolic. And so what dynamics of parabolic are known to be impossible. So this is a very, it's an open problem. What are the dynamics? Maybe it's going to be interesting. Now, another reason to study it, which we discovered as we worked through it, is that these flows generate a tree type structure. And over the past, say, 10 years, thinking about it, I've thought of the analogy with a self-similar group, where you take the Cayley diagram for the group and re-embed itself further down the tree. So these flows have a dynamical system property that looks like a self-similar group. Well, that's really interesting if it could be made legitimate, mathematical, because self-similar groups, you can do a lot to classify them. That's a big project. And so you could ask, what about aperiodic flows? Can we approach them using some more tools? Not just construct them, but sort of discuss what do they look like? What are their dynamics? So that was immediately addressed in papers by Etienne and Shigenori, that I think Gieser commented that Katak's famous theorem in 1980 about entropy and periodic orbits implies that an aperiodic flow has zero entropy. Well, it's not hyperbolic, and it doesn't have fixed points. Holonomy, it's not what you call elliptic. It's not preserving a contact form. So they're interesting class, which is not generating a lot of contraction, but it does have some non-trivial holonomy because it doesn't have fixed points, and it has these translations that Christina was thinking about. Now, other theorems were observed that there's a unique minimal set inside the plug. Well, here I put M. I should have put P for the plug, because you might have several plugs if you want to do that. But anyway, you have one object that's a minimal set, which has this, every orbit is dense. So maybe the structure of the minimal set is the key to understanding these. So there's a unique minimal set. Then in a paper by Shigenori, he observed that there's, much like in the picture of Wilson, where you have, I'm going to see if this works. Let's go back to Wilson, and then you'll get dizzy from popping this. Here at the bottom, you can see all these orbits going up to the point P and leaving point Q. These are going to be attracted to the point. And if they don't hit the point, but they spin around and limited on the circle there, in the suspension, you get a circle, well, they're going to be wandering points. So the other thing you get about the dynamics, if we go back, is that the open set of wandering points means that these can never be measure preserving. So you have a highly irregular flow without periodic points that is outside the usual set of techniques. So this is the background. This is, people know a lot about these. So about wander sets, but they don't really know about minimal sets if they're not hyperbolic. If you don't have some linear contraction to work with, your tools come up empty. So here are the papers. Similar Bobaki by Gis, a paper that was translated by Matsumoto. It's a very nice paper too, with lots of commentary. And then Greg and Christina had a second paper where they generalized their construction to many other cases and contains other ideas about the construction. That is, I'm not sure I understand them all, because Greg likes to think of these as some sort of computer algorithm. He thinks of it as a computer program that never terminates. So he obviously uses Windows and has lots of spinning dials in front of him, because that's his picture of these flows. There's an algorithm that will not stop. And so these are the three background papers. I can't see the audience, so I don't know if everyone left yet, but let's go to the next slide. So when you look at this, you can ask, what is going on? Why? I know Katak says there's no entropy because there's no periodic orbits, because there's no hyperbolicity. But why is the entropy zero? Meaning, if you think of entropy as counting the growth rates of separated sets, can you count this growth rate for these aperiodic flows? Sounds like a hard problem. It is, but it's naive. And so you wonder, can you actually do that? Well, we'll see. Other one is obvious. You have a minimal set. And in the paper by Etienne, he makes an argument that the minimal set is two-dimensional. And we'll see why that might be in a second. But the question is, in general, how would you show that a one-dimensional flow has a two-dimensional closure? So that's a basic question to answer. And then as a further question like that, you can look at the topological shape of this minimal set. And yesterday we heard Christina talk about shape theory, and I'm not going to say too much more, but shape is this powerful invariant that if you look at it in terms of certain types of flows, like Morse-Smale flows, it very much corresponds, say, to the isolated blocks of Conley. So shape theory has a tool, but can you use it to analyze the shape of a minimal set in a Kuperberg flow, or more generally, aperiodic. So shape is its own world. Here's my one-page definition that the circle and the Warsaw circle have the same shape. And that's because they both, if you look at an open covering, they both look like circles. And more technical definitions can be made, obviously. But the general idea is you want to know what the approximate, another way to define this is just take covering by little disc and form the simplicial complex of the nerve and ask when are the two nerves of the objects going to be homotopic. That's it. I think that's equivalent. Certainly the idea of shape is it's a concrete form of homotopy check theory on the level of homotopy. So for example, if you look at a minimal set in a torus, you know that it's transversely cantored, but more importantly, if you take out one point, you can find a point that does not hit the minimal set. It's in the complement, open complement, and what is left retracts onto S1 cross S1. So this that's exactly what you see in the picture of Paul's example. And that when Paul constructed it, his immersion is actually of a fattened version of this wedge. And that's characteristic. In his example, the minimal set is exactly Dangerois, and that's shape theoretic to a wedge. So shape has something to say about the example that Paul constructed. Now, what happens in the case of the Kuperberg? Well, that was the problem that Christina had posed. And when Anna visited Chicago in 2010, that was the project. Can we analyze the shape of the minimal set? This turned into a multi-year project lasting long past when she had left Chicago for Strasbourg. But we produced at the end this 200 and some page manuscript that is published in Asterisk, where we analyzed all sorts of properties of the Kuperberg flow. And I'll describe that next. Then later, there's some other constructions that we added. We stopped at 2016 because we solved our initial problem. But there's a lot more you can say about these flows, and we added some more. Now, one thing that I'm going to talk about today is that we then ask about what happens when you perturb the Kuperberg flow. When you perturb it, you don't expect variations to be aperiodic if you just perturb it in a general C1 way or C infinity, but there's some interesting things that go on, and that's what I want to describe today. So our results, well, let me describe what I mean by perturb, and then I'm going to state some results. So our results depend upon a generic hypothesis, and we've heard generic used in talk several times, so it's not a bad word. But it does mean that we can't do it unless we make some strong assumptions. One is that if you look at the embedding that Christina uses, where she takes the two-hold the punctured torus. Well, it's an annulus, and she pulls off the horns and then inserts them into each other. I've drawn this periodic orbits in the Wilson plug, and you're making it so that these periodic orbits just touch. They're transverse to each other, and they touch at a point, P1, well, it's interior. That's the picture. And it's always drawn very nicely so that it looks, pleasant, so you're not scared by it. Well, that's a generic condition. If you look at it in a cross section, the graphing is always a parabola touching a line. Two smooth curves crossing. and they touch a quadratic contact point, because why make it more complicated? Well, that is a generic assumption, because her example works for any sort of embedding like that. There's a condition, which I won't go into, called the radius condition, which forces the aperiodicity. And it's true for a large class of embeddings of the handle into the core of the Wilson plug. So this is what it looks like, and that's generic. The other assumption one makes is that you have a Wilson plug with a vector field climbing up to the periodic orbit. Well, there's no description of how it climbs. It just has to have an asymptote. So this is starting to look a little bit like the problem with smoothing foliations. I mean, all we need is a climb, but you could assume the climb is quadratic, meaning that the vector field vanishes to second order and not to 10th order or infinitely flat. These are two assumptions you make when you see a picture of Christina's construction. And I call them generic conditions. They're spelled out more technical stuff in the work with Anna in the book. But if you make these assumptions, then you end up with theorems. That was the key point, is not just to know these constructions by heart, but to actually be able to prove things about them. So first thing is the amazing fact that the minimal set is a lamination. Now, this was stated in a paper, the seminal by Etienne, and there is an approach to proving it there using genericity. We wanted our stylists to just prove it directly, just hands-on, why are they equal? And that really depends on the quadratic approach. If you only assume C1, then Greg has examples of the construction of Christina where the minimal set is one-dimensional. So this two-dimensionality is very much dependent on the whole thing being C2 at least, probably more than that. The other thing we're able to do is show that the flow not just has zero entropy because of Katak, but we're able to calculate an estimate on the epsilon growth of epsilon separation, the growth of epsilon separated orbits. And you find that it doesn't grow at an exponential rate, because that would give positive entropy, but it grows like exponential square root of time. Well, bounded by that. I don't think we got a precise estimate, but we showed at least the square root of time. So there's some hyperbolicity in the system, only it's not hyperbolic. It's growing at a square root of exponential rate. That's one of these great, I would seem very mysterious, because usually slow entropy, like with shift spaces, means polynomial growth of epsilon separated. But here it's intermediate. So this takes a lot of work, and again, not going into that because I want to encourage you to buy the book, the Asterisk volume. I'm sure it's on sale by now. And our third result is that the minimal set has unstable shape. Now that means something very, you think, well, what shape? It's going to be some approximation system. More precisely, we have a shape is defined, we have a chain of open neighborhoods of the minimal set. And if you look at the fundamental group of these open neighborhoods, and they each have retract properties, the rank of these groups is unbounded. So unlike the case of the Seifert of the minimal set, which is a wedge of two circles, there the rank is 2, constant. But here the rank expands, it explodes, in fact. So these are our results, and we were happy about it, but we had put a lot of time into it. And so the next step was to give the problem to a student. So I asked my student Ingebretson, Daniel, to look at the Hausdorff dimension of the sets, because that was not addressed in any of the previous works. And the problem is that you have to make assumptions and you get a number, and the number is 2.6 something, except that's with all his conditions. What he really shows then is that it's bigger than 2 and less than 3. More precise, it depends. So it's somehow, when you have slow entropy that's partially hyperbolic at some square root, you expect the Hausdorff dimension to reflect that somehow, and this is what it does. So these are our results, and then the problem we didn't want to touch is what happens if it's not generic. Because there's a lot of flows you can build by changing the speed of the Wilson flow or by changing the shape of the insertion. And when you do that, the estimates that Anna and I used become problematic. I mean, it probably can be done, but we were already at 200 pages. So that's one of the open problems, is simply there are a lot of aperiodic flows out there. So what else can you say about them without devoting many more years, one hopes? So in order to say more, let me go into just a recall of the lamination that is inherent in the Kuperberg construction. I mean, this is a picture that was in Etienne's Seminar Bourbaki, and it's the fact that when you do this insertion, you're taking the Rabe cylinder between the periodic orbits, which are pictured here. It's R prime, but there's a hole where the insertion is going to hit this orbit. And so it's going to cut open that periodic orbit at top and bottom. And this is an annulus. What you have is an annulus with drilled annulus, is I think the phrase. And then that is going to be reinserted. And when you reinsert the annulus into itself, it looks a bit like this. And now your flow is going to be switching between the annulus and the insertion, and this is going to be happening forever. And when you do that, what you're finding is that the flow of that annulus is what we call M0. It's a surface, it's an infinite surface, and its closure contains the flow of the periodic orbit. And so the minimal set is contained in the closure. And so the question was, if you want to show the minimal set has some property, you could try to show, see, this is sort of like looking at a flow and a torus of irrational rotation. You know, you close the flow on a torus with irrational rotation and you get the torus. Is there a Dangerois theory for these flows? That's one nice way to put it. But what we end up proving with a bunch of delicate estimates is indeed, for generic, they're equal. That means that the minimal set of just a simple flow is a lamination, except the problem is that the leaves have boundary orbit that's dense in the whole system. So this is not a foliation like Larry or me or anybody would be happy with, because it's got very bizarre geometry. So the boundary of every leaf is dense, so we call it zippered, but nonetheless, it's two-dimensional. And so these are our theorems. Now, let me see if I can, one more thing about this, is that this flow can be drawn out as a picture. And when you do that, you end up getting a tree. Now, the tree is not a normal tree because you've got these plugs, the notches, and when a knot hits a notch, you go around the cylinder again. So these sections of this tree are pieces of that cylinder. Now, the closer you get to the cylinder, the more times it intersects the notch, and so the length of the tree, as you go down it, the branches get bigger. And so you end up getting not a good old-fashioned calligraph of something, but you get something that's been pruned. It's been clipped off. The closer to the core, the shorter the branch. But if you keep going down, the growth rate, if you're following, say, generic with quadratic approximation to the Wilson flow, the number of branches will grow quadratically or linearly as you go down, and the length of the path needed to get around all these branches grows quadratically. So this is the picture that Anna and I developed that gave us the insight to most everything we were doing. Because with this picture, you can estimate many properties because the lamination of this cylinder is a solid object and the flow is sitting inside of this thing. And so if you want to estimate, say, the flow entropy, you estimate the foliation entropy of this laminate. So you bring in tools from foliation theory, which we understood a little better. So, but the Kuperberg principle says the tree structure, no matter what happens, is going to be copied repeatedly because the branches here are getting closer and closer together, so they're following each other in holonomy for further and further time. So you get ideas of foliations being applied in a highly unique way. Now, one thing I like to call it is a scaling function, that there's something I won't try to draw, but this Wilson orbit is converging to a periodic circle. This is driving, this generates the holonomy of a path, flow line, following down that tree. You think, what's happening transversely? Well, what's happening transversely is what happens as you approach the periodic orbit of the Wilson plug. And so in the sense of hyperbolic Cantor sets, you can define a scaling function. And that scaling function is, it's not going to have hyperbolic expansion. It's going to be some, well, it's going to be quadratic, but you can estimate it and get control over things like the entropy. So those were our techniques. And I wanted to emphasize them because I think there's a lot more play, a lot more use for these things if anyone has the interest in developing them. So that's what I said, is that the tree, as you go down it, gets closer together, so it shadows itself, and that's the self-similarity I was referring to earlier as parallel to, say, self-similar groups. The area of the tree is quadratically is sub-exponential. Look, trees should grow exponential, but the number of branches that you can reach grows at the square root of time. So this is how we estimated entropy. And the same argument lets you estimate the covering dimension of the minimal set transversely, and that's what Daniel Ingebrigtsen used. So there's a lot more results if you have a reason to pursue this, because I think that aperiodic flows are mysterious, but there's I think the Kuperberg principle that they have to have this translation, which in a compact setting means there has to be some contraction of the transverse holonomy. this is a tool that can really be exploited further. Anyway, so what our other project was, is we asked, well, if you take a dynamical system, you would like to know, is it robust? You could try the Pallas conjecture. Is there any genericity to these things? What happens if you perturb it? Well, if you perturb these, I'll show you the construction, but we call it derived from Kuperberg because it's derived from a Nossoff. You perturb a Nossoff. Well, derived from Kuperberg, you can get two possible things you could do, and I'll show you both in a second. You can perturb it where there is where the two cylinders don't touch, and then you don't break open the periodic orbits, but what you do is make them longer and longer the closer you get to contact. So the perturbation on one direction is again periodic, and what's interesting is it looks a lot like this theory of compact foliations developed in the 70s by Sullivan and Elmer Vogt. So on one side, you have compact flows, compact orbits in the plug. On the other side, though, you end up going too far, and when you do that, you end up generating horseshoes. And now once you have horseshoes, you know the game is up because they have periodic points. You're no longer an aperiodic flow. But you also have positive entropy. You have hyperbolic exponents. You can estimate Hausdorff dimension. And so this flow sits between one direction, tame, just closed orbits or nothing fancy, and on the other side, a whole spectrum of little tiny horseshoes, all converging. As this epsilon goes to zero, all these horseshoes are spinning out to give you something that's not hyperbolic, but it's aperiodic, and it's fascinating. So this is the other result we got. Now, how do you do it? Well, I just said this. You take the rate flow and Kuperberg insertion and perturb it, and let's see how that happens. First, this is the goal. We want a picture that looks like this. The details are in our papers, so we don't need them. But we want to get a horseshoe. Classic horseshoe, you want to fold and insert. So with that as a definition, you go and look back at the original idea. Now, this picture doesn't help you a lot with analysis because it's a plan for insertion, but you take the flow on this cross section you see, the R0, and when you insert there, you can draw that as a pseudogroup acting on that. Now, the problem with this is that the pseudogroup, the flow lines, you're not seeing it, but it's not always transverse because it reverses direction if you look between these 2 points. When it reverses direction, there's a contact line, a center line, and then you don't have a perfectly happy pseudogroup because the pseudogroup has discontinuities. But nonetheless, I think it's a new way of using pseudogroups, and it allows us to correspond dynamics of this broken pseudogroup with this tree, which is called M0. So we want to convert the self-similarity of that into a pseudogroup property. And so that's the, I introduced 2 maps, which are the key maps in this game. And let's get the picture. One map, this flip, is the insertion, fold and insert. The other map is climb up, and that's the Wilson map. So anyway, that's our plan. I don't know on time. I think I've got a few more minutes. This looks like you're doing something of a ping pong game where you're back and forth, but there's only one player and he's hitting it against a wall. and it keeps bouncing. Plus, there's this issue of how do you go up? It takes a long time to move. So the time is action's too slow for entropy. But the idea of a perturbation is what happens if you take the insertion, which is a contact, should be tangent in Christina's business. If you go one side, they don't touch. This doesn't break open the orbit at all. If you go the other way, it looks like you got clumsy and you went too far. But this other way is over-inserting, positive, epsilon. And when you do that, you get a picture like this. Now, this picture is not, these are all hard to draw, so it's not accurate 100% because you over-insert, but then this climbing picture is flipped and keeps reinserting itself. And that's what the next picture, and now I point out this is one, you can do this for any element in this profinite group associated to the shape of the minimal set, shape of the solar M, the lamination. But this is what you're after. You're after a picture that looks like a horseshoe. And the reason why this looks like a horseshoe is that you then take this picture and keep it iterating it, and you get a local picture. This insertion is up above the axis, and now when you flip it, you get this picture. Now, when you get this picture, that starts to look like our horseshoe. And so, if you do it again, you find out that you're all of a sudden generating iterations of this, well, it's half a horseshoe, but it has the hyperbolic property. Because you've taken you don't travel all the way to the Wilson circle, you start limiting at points in between where there's linear contractions going on for the generic case. And when you do that, all of a sudden, all these points, beta, alpha on the screen, they're going to be periodic orbits in there because this is like the intersection of a stable and an unstable manifold. And so in there is going to be a periodic point with positive and negative and exponents bigger and less than 1. So all of a sudden with this picture, you see horseshoes generated. Now, I've not explained, and it's just an advertisement for the work, I guess, where these maps are, but there are plenty of these return maps and climbing available to work with. And for each of them, you get to build this picture of a horseshoe. So when you do that, you've realized the exponential growth of orbits, and you realize the chaotic behavior, all for very small epsilon, very close to the aperiodic flow. So I like hyperbolic systems, but this is a business of what happens when they degenerate. And somehow when you get near to the Kuperberg or aperiodic flow, you wonder, is this what always happens? Because aperiodicity is so unusual. It's such an unusual property. So no periodic orbits, it means it's not contact, it's not hyperbolic, it's parabolic in some strange dynamical sense. Do you always have horseshoes? So the question, I don't know how to nail this down, but it seems plausible, is that you could wonder in this example, well, you might calculate the dimension of these or some other properties of these returns, but that's going to be really fuzzy because you're making a lot of assumptions without being precise about the return maps and their exact. Now, in the paper with Greg and Christina, he actually works with polynomial equations. So in that case, you could probably do it. You could perturb the polynomials, and if you had enough computer time, get calculations. But when you see this, you somehow wonder, and this is why I like to call it a principle. If the flow is aperiodic and therefore has to have a translation, can you find it? Can you find the aperiodic net and aperiodic flow, the contraction axis? That's basically the issue. And then find an element in the return map that pulls the orbit along that axis. If you can, that gives you this map, psi, in the previous slides. The other map, phi, is just a return map from the periodicity, the fact that it's a minimal set. And so the question I'd like to pose is, excuse me, is this generic? Is this the picture for an aperiodic flow? That nearby, if it's C3, C1, this fails. Well, Paul's example, the minimal set is the Angevin minimal set. Greg has piecewise C1, and its minimal set is probably complicated, but it's certainly not two-dimensional. But C3, we know from foliation theory, means that there's a lot more restriction on how things can limit to other, how a pseudogroup behaves. So maybe not C infinity, but just C3. And then you also have the work that's in Jenny Harrison, where she says her constructions probably can't go to C3 for reasons of Hausdorff dimension. I can't tell you how that relates, but again, it somehow suggests that C3 is a barrier, and so can you turn it around and use C3 to show that near an aperiodic flow, you must have horseshoes, which would be, I think, an interesting statement about what's going on with it in this world of dynamics. Or if you want to give yourself more, there you can bring up the unstable shape property, because that implies that your orbits are already unstable shape. If you close the orbits to get a minimal set, that implies the orbits are already wild. They're wild. They have an infinite set of generators. So there's obviously a lot going on at some micro scale. So in any case, I think there's more to say about aperiodic flows. Anna and I did work. She's in Strasbourg. It's harder to collaborate, but it's also, this is takes a lot of time to get ideas. And we worked on it. It's been 10 years now. And I think Paul's example is 70 to 20 is what, 50 years ago. So maybe in 10 years, maybe have a better understanding of these. But I think there's a lot of richness. Paul set off a subject. He set off an exploration where there's a lot of unexplored territory. So I thank you, Paul, and happy birthday, feliz aniversario. I don't have any sound. Okay.
What's happening? I think we lost.
What?
I think we lost.
Lost Brazil.
What?
It seems so. We'll say we lost Brazil.
Oh, you lost Brazil. I found the audio.
Let's thank
Well, I'll leave the picture of Paul up. Isn't this?
So for this small audience, let me say just thank you, Steve.
Steve,
Wow.
can you hear
You
me?
know, the
No,
worst thing,
I should thank both of you for
Steve.
this. I'm not talking about the talk right now, but for the work, for the whole work that you put in. Thank both of you for this. I'm not talking about the
Steve.
talk right now, but for the work, for the whole work that you put in. Thank both of you.
Uh-oh, we're in some kind of echo chamber.
Steve, can
Right.
you hear me?
Sim, pecou. Sim, pecou.
So what happens now?
Well, I think I've stunned the audience into,
So what happens now? Let me see what, would
well,
that be on YouTube as well?
into,
Let me see what. would that be-
Can you hear me?
yeah, now we can hear it.
We have a technical problem.
Hold it, how much of the talk was blunt?
Are
How
not
much of the
working.
talk was technical?
So there's a reverberation, but I wanted to say something.
What's that echo?
Yeah,
Like a set of similar tree structures.
Oi, tá funcionando aí? Tá? Eles estão ouvindo lá?
eu estava tentando falar. Agora está me ouvindo? Tá bom. Então, tivemos dificuldade com microfones, mas como? Okay. I'm sorry. I was trying to speak, and this confusion with the microphones left us a few minutes without being able to function. 2 microphones not functioning. But I thought it would be appropriate for me to say something about how I came about seeing that counterexample to the Seifert conjecture. It often happens in mathematics when you're working on a difficult problem that you look at some similar problem that's easier to solve. In my case, I wasn't exactly doing that, but I was working with codimension 2 foliations on 4 manifolds and trying to see how you could perturb them, how you could modify them. For example, take the product foliation of this 2-sphere times the 2-sphere, the 2-sphere time a point. And I was trying to see how you could modify that. And it became clear that you could use a flow in the transverse direction to modify it. And if you went far enough, that would destroy the sphere leaves. Once I had seen that, it was a very natural question to ask whether you could do that in a 3-dimensional manifold. And then Danjois was obvious. So I think I was quite lucky to have that happen. I was working on another problem and it just gave the answer.
Some question. There is another question.
Hello, I have a question about. My question is the following: if you start from a dynamical point of view, if you start with dynamical system on a disk, like a 2-dimensional disk, a dissipative system on a 2-dimensional disk, and like something like a Heenan map, for example, and then you can have examples of a Heenan map that has 0 entropy, and the minimal set for the map will be will have 0 entropy and will be a minimal aperiodic set. And my question is if you can suspend this map to a flow that will have something similar to the Kuperbeck flows.
I think I'll toss that question to the audience.
I can say, I don't think it will be similar because this example of this aperiodic flow, it really uses 3rd dimension to produce that minimal set. In a way, it's And starting with something in the surface, I don't think it will give any results similar to that example. That's how I feel.
But is it possible to suspend the two-dimensional diffeomorphism of a disk and embed it in a flow so that you still have the minimal set will be preserved of the two-dimensional disk? Maybe it'll be a different type of example, but is the construction possible? Like if you take a two-dimensional diffeomorphism of a disk which has zero entropy, and then you can suspend it.
You can suspend that. Can I say something? You
do
can suspend it. You will get the minimal set of the non-map that is aperiodic, but you will also get a lot of periodic orbits nearby.
Why would you get a periodic orbits nearby?
Because of Brouwer.
Because of Brouwer.
Brouwer was the problem.
Yeah, no, that's, I don't know. I'm gonna go back. That's the quote that Christina kept to herself. Let's go back. Oh, come on. How far back?
But maybe we can ask Paul something. Paul, can I ask you something?
Yes, fine.
When Steve and I were working on the Cooperberg plug, we found a paper, I think by you or by someone. Do you remember this paper, Steve?
Can you hear me?
Yeah, you remember the paper? We found a paper where I think you were trying to prove that it was impossible to build an aperiodic plug. Is this true or?
Oh, using some shape theory.
Yeah.
Well, Handel had a paper in the Annals where the flow, if it's separated, it's isolated minimal set in the sense of conway, then it's carried by a surface. And so it's got to be a Seifert minimal set.
So, well, maybe my question was, what did you, Paul, did you thought, I mean, in the time between your construction and Christina's construction, you thought that an aperiodic plug existed, or you thought that it didn't exist?
I don't think I know that paper you're talking about. It wasn't mine.
Oh, it wasn't yours. Sorry.
But yeah, it's people tried, I guess, to generalize your construction, right? Or
That's
to
true.
modify
It
it
was
or something.
natural. And Jenny Harrison, in fact, had a very, very difficult argument to make it to get a C2 counterexample using technical properties of Whitney, approximating mappings.
But again, her example was started with the Seifert model and then did like a three-dimensional modification of it.
Yes.
It looked very, so she got something very wild, not two-dimensional as a result.
Right. I have no idea what her minimal set or sets look like, really.
Yeah.
Sorry, we are almost running out of time, so probably we can stop here. So, thank you, Steve, again. It was a beautiful talk, but we have no time for more questions. So let's thank the speaker again. Also,
Well, I'm on room view. I can see who clapped. But thank you all. Thank you for listening.